So, hello everyone. In this course, we will learn about extremal graph theory. And I will assume that you already have learned about the materials in the Introduction to the Graph Theory course. And you are already familiar with the basic concepts on the graph. So what is extremal graph theory? So here, it's about the relationship between graph parameters and graph properties or graph structures. And usually these graph parameters are expressed as a number. So this is a quantitative parameter. Then it makes sense to consider about its extremal value. So if you consider certain graph property or structure, let's say certain class of graph, and among those graphs, and we consider certain graph parameter, what's the maximum value of that parameter in that class, or minimum value of that parameter in class? So that's what we study in extremal graph theory. And that's why it's called extremal, to seek the maximum or minimum. So you learn about extremal behavior of graph. So in many cases, it mainly concerns about the relationship between parameter and some structure. So often what it shows is that if this graph satisfies its graph parameter is at least something or at most something, then can we find a certain structure, this desired structure in a graph? In other words, if you take the contrapositive, if you don't have this structure, then this parameter is at most something, or at most something. So that's quite common theme in extremal graph theory, and most of the things that we will learn this time is also regarding this thing. So what about, what's the most simple case? What are the most natural parameter that we can consider? And one of them is this Turan number. This number of edges. A very natural parameter is number of edges in the graph. And a very natural structure we can consider is subgraph. More specifically, specific subgraph. You can consider specific graph like a triangle or path of length 2 or K4, etc. If you study about the relationship between this parameter, the number of edges, and the subgraph structure, then you will get what's called Turan theorem. And we will talk about that first. Okay, maybe before going to the Turan theorem, I will tell you roughly how we will proceed. So in this lecture course, in this course, we will divide the topics into several parts according to the size of structure that we are looking for. We consider small structure. So as I mentioned in extreme graph theory, when you have a graph, if it satisfies certain parameter or certain condition, can you find a certain structure in a graph? And this structure could be very small compared to this G. For example, we may assume that this G has n number of vertices, and that n is arbitrary, and then you are only looking for this triangle, which consists of 3 vertices. Then this structure is small, and this graph is large. And we can consider, say, small structures and, let's say, not so small structure, and a large structure. So we will consider these topics depending on whether the structure that we are looking for is small, in other words, fixed size, and not so small structure, which means that the size of structure that we are looking for is, say, if you have n vertex graph, can you find the subgraph with square root of n vertices or log n vertices? So there are some quantitative relation with the size in G. That's here, and a large structure is like near spanning or spanning structure. In n vertex graph G, can you find the Hamilton cycle, which also consists of the n vertices? So it has size comparable to the original graph, so which is like finding optimal structure. So we will consider those themes, and we will start from small structure. And as I mentioned, most natural parameter for us to consider is the number of edges and specific subgraph. So by considering this relationship between these two, it's natural to define the extremal number or Turan number as follows. This is, we already have covered this topic in the introduction to the graph theory. So, but I will repeat some of them. And while repeating it, I will try to provide a different proof from the previous course. And we will also extend the concept into more general concept than before. What can we consider? For a graph F, we define the extremal number or it's called Turan number, and we usually write as ex and parenthesis nf. This is the maximum number of edges in an m vertex graph that does not contain f as a subgraph. So this is the maximum number of edges in an m vertex graph having no f as a subgraph. So if we know that your graph has more than this number of edges, then you are always able to find the copy of f in your graph G. So oftentimes, when we want to find f inside of G, we will say that G is host graph. that we want to find the structure that we are looking for, and we say F is guessed graph. We want to find this inside of here. And this name kind of is motivated in a way that we think finding F inside of G as embedding this into here. We want to put this F into G. We assign its vertex of F to vertex of G so that all the edges correspond to the edges. In that way, we are putting this in here, so this is post, this is guessed. So, and we have learned in the introduction course that the Turan proved the following theorem determining the extremal number of complete graph. So if you have a graph that does not contain k sub r plus 1, and it's an n vertex graph that contains at most, let me copy and paste here, that have at most a small t of r and edges, and I will explain what it is, and the equality holds only for capital T sub r n. So natural example that does not contain n k sub r plus 1 is r part-type graph. So all the edges are between two parts where the vertexes are partitioned into r parts. This does not contain K4. If you choose 4 vertices, 2 of them belong to the same part where the edge between them is absent. So it does not contain such a structure. And you can maximize the number of edges by making it as balanced as possible. The sets have the almost same size. And then put the all possible edges between. Since that's a very natural graph, we give name of this capital T sub r n is be the balanced complete r part-type graph with n vertices, and we write down the small t sub r and be the number of edges in this graph. This is called Turan graph. And here balanced means that the number of vertices is as balanced as possible. If number of vertices is 10, then you put 3, 3, 4, so that the difference between the largest one and smallest one is as small as possible. And that difference is at most 1. So this is what we have learned about. And indeed, we extend this definition to hypergraph. And we also learned about hypergraph in the introduction to the graph theory course. And there, how do we define if you have R uniform hypergraph? That is the tuple or vertex and edge set, where each edge consists of the set of size R subset of V, and V is the vertex set. And we simply call them R graph. With this definition, graphs are just two graphs. And extending this definition of extremal number, we can define the extremal number of I graph. So if you have I graph F, we again define this extremal number Ex of N and F as following. So what would be the natural way to define? So extremal number of F is the, again, maximum number of edges in an n vertex R graph that does not contain F as a subgraph. And moreover, if you have more than one graph, if you have a collection of R graphs, so calligraphic F is a collection, then we say that the extremal number of this collection is the maximum number of edges in an n vertex R graph that does not contain any copy, any graph F in this calligraphic F as a subgraph. In other words, if you have a graph with the number of edges bigger than this extremal number, then what? Then you should be able to find, you are able to find at least one of these. Not all of this, but at least one of that inside of G. Okay. So this extends the definition of extremal number to hypergraph. And let's consider a very easy case about K22. So this is the graph K22, which is same as C4, cycle of length 4. And what do we know? This we can show that it's roughly half graph 0, 1 and n to the 3 over 2. That's an upper bound. And proof is very standard by counting the number of copies of K12. Oftentimes I will just write sharp, which is short for the number. Okay, so how does this look like? K12 as this middle vertex. So how do we choose? Let's say M is the number of edges. We choose the middle vertex first, and we count the choice of the other two. Then what? We have this. For each vertex, we choose them, and then among its neighbor, you choose two of them. Then you get this copy of K12. Okay. And this is the number. And what do you know? Because this function fx is x choose 2, x minus 1 over 2. So this is convex. Then, using this convexity, we know that this holds. If you have convex function, what do we know? You take the value and then take the average. It's bigger than you take the average of these two and then take the value. So here, what? If you delete 1 over and here, and that's what? That's average value corresponding to this blue one. And then this is what? You take the average and then apply the function which correspond to the red one. Then this is what? You can, the upper one is 2 times number of edges over n and choose 2, and then you can check that this is like same with 2 times m squared over n minus m. But what do you know? If this G has no copy of K12, then the above number is at most n choose 2. Why? If it is more than n choose 2, then otherwise we can find 2 copies of K12 using Turan principle with what? Distinct middle vertex shooting both ends. So if you have this, then you count this pair. And then another, then you count this pair. And another copy, then you count this pair. There are at most n choose 2 pairs to count. If there are more than n choose 2 copies of K12, then some pair must be counted twice. Then what? In that case, 2 of them count the same ends, so we get the K12, K22. This yields a copy of K22. Hence what? Hence, we know that this number is n most n choose 2. And solving this gives this. This is just a quadratic equation in terms of m. You just solve this, and we get this as desired. So we have this number, and then we should roughly half times n to the 3 over 2. Instead of counting K12, we can count K13 or K14, etc. And that yields that the extremal number of complete bipartite graph is you can prove an upper bound. Only. Okay, so we have defined Turan number, and then we show the Turan number of complete bipartite graph. This is called Kobayashi-Turan theorem. So here is to that. And we will talk about, so this is upper bound. This big O notation means that this is at most some constant times the expression in here, where the constant may depend on T and F. And later we will also try to get some lower bound on this number. Anyhow, so we have this theorem, and now we will use this. So this is for bipartite graph. And then using the similar argument, we can show theorem regarding R graph, which is also R-partite. And we'll discuss that in the next video. And we will define what's called the Turan density and then discuss about this hypergraph Turan problem in the next video.